So in this video, we're going to take a look at our big takeaways in regards to linear equations from the course. So we'll start off with a big idea. Equations, they tell us that two quantities are equal. And if they contain variables, then we can figure out what that variable would be. So 5 is the same as 2 plus 3. So an equation could say 5 equals 2 plus 3. But that wouldn't give us much to do. It's just telling us two things are equal. If it said 5 equals 2 plus x, though, then we would have enough information at our fingertips to figure out what x was, because there's only one number in the world that could make 2 plus whatever we're talking about equal to 5. So that's where we start, and then we'll look at this in a real world example. So Tina, who is 39 years old, is 5 years more than twice as old as Maureen. So it sounds a little bit complicated, but at its core, two things are equal. Tina, her age, 39, is equal to, well, it's not equal to Maureen's age, but it's equal to some combination, some calculations done to Maureen's age. So this could be represented with an equation, because we know that two things are equal. 39 is equal to an amount that's 5 years more than twice as old as Maureen. So the equal sign tells us that this is going to be an equal amount. And then a description that says 5 more than 2 times Maureen's age is 5 plus 2 times, and now we don't know Maureen's age. So we could use a variable at that point. And the idea is, once you have an equation that you know is true, or if someone hands you an equation that you assume is true, then at that point, you have enough information to figure out what one value of the variable makes this true, usually. So it takes us to our next big idea, because the next question is, well, how old is Maureen? So to find out how old Maureen is, basically it comes down to solve for m. And how do you do that? We're going to take this true fact, and we're going to use balanced inverse operations in reverse PEMDAS order to create simpler equivalent equations. And our simplest equation that we get at the end is going to tell you m equals blank. That's going to tell you m, Maureen's age, is this. So we will have figured out what the value of the variable is based on balanced inverse operations. So what you have to do is reverse order. So adding and subtracting is the last thing that happened to m before it became 39. First it was doubled, then it had 5 added, and out came a 39. So if we're trying to figure out what m started as, this piece should go away first. And an inverse operation for addition is subtraction. So if you have two things that are equal, and you decide to take 5 away from each of those things, you're not going to have 39 anymore, you're going to have 34. But on the right-hand side, if you also subtract 5 from there, you're going to have something that is equal to 34. So 34, based on the inverse operations canceling, is going to equal to 2m. And this is where learning to write an equation down after you've done something to both sides became really important, because now you have a simpler equation to work off of. You have a simpler equation where the inverse operation that you're going to need now is going to undo that times 2. That sounds like a job for division, and we'll divide both sides by 2. And those guys cancel, and we'll find out that m is the only thing left on the right-hand side, because the inverse operations have canceled so nicely. And on the left-hand side, 34 divided by 2 gets us 17. So apparently, Maureen was 17 years old. Next big idea. That last one, there wasn't much to do besides jump right into inverse operations. But this big idea admits that it might be necessary to simplify expressions, or maybe use inverse operations to get a variable off of one of the sides, if it's on both sides, before this reverse PEMDAS becomes easy to apply. So if you get something that looks a little bit more complicated, remain calm and think, if I can simplify one side or the other, and if I can remove variables from one of the two sides, then the equation won't look any more complicated than the one that had Maureen's age in it. So we apply the things from the first video, like look at the left-hand side. There's another way to write 3 times the quantity 2x plus 8 minus 8. We can simplify the expression over there by multiplying the 3 times the 2x minus 8, which takes distribution, and you get 6x minus 24. And if 3 times 2x minus 8 was equal to 4x plus 16, which the equation told us it was, then any version of that would be, so we can just carry down the right-hand side. Now we're going to use inverse operations to eliminate variables from one side. We handled the first equation with Maureen's age very nicely, because there's a variable on one side only. So a variable on two sides is an obstacle. We should take care of that right now. So if we could figure out a way to remove either the 6x from the left side or the 4x from the right side, then we would only have a variable on one side, and we'd be in good shape. I tend to move the fewest, because I can remove 4x's from the right-hand side. but I would have a different amount on one side or the other unless I did a balanced inverse operation. So I'm going to do it to both sides, and that leads me to this. So at this point, it's the Maureen problem, basically, where I can do inverse operations to this guy, add 24 to both sides, get the result. Left-hand side cancels, right-hand side becomes a 40. Now I have an inverse operation I have to use for the 2, so that looks like division. I'll divide, and we get x equals 20. Okay, so look at the big idea again. You might have to simplify. You might have to use inverse operations to get a variable off of a side. But at a certain point, you get to a simpler equation that you feel like you have complete control over. Next big idea is you can show that a value is a solution by substituting it for the variable and then simplifying. So we just made this claim that this first equation they gave us is steering us to the decision that, well, 20 is the x value that makes this equation true. But there's no evidence up here unless you believe the work that we did. So what we can do instead is we can check our work, basically. And we can take the equation that they gave us, and we could say, look, I'll show you that x equals 20 is a solution by substituting 20 in everywhere that x was. So there's no mystery in this equation anymore. You're just trying to say, look, I used x equals 20, and it's a good result. It's a good match. It makes the left side and the right-hand side the same. Now, I can't tell if they're the same yet, so I'll go through PEMDAS, order of operations, and evaluate both sides. The 2 times 20 happened, the 4 times 20 happened. Now I think the parentheses has to happen on the left-hand side. Right-hand side is now 64, and then 3 times 32 happens in 64. So yes, we just showed that x equals 20 is a solution. 20 was shown to be the value that makes the equation true. So up until this point, we've worked with equations that only have one solution, Maureen 17, the 20 that we just found. But the last big idea for this video is some equations are not true ever, regardless of the value of the variable. And other equations are true no matter what value is used. So you wouldn't get a result like this unless x equaled 20 and that was the one value of the variable. You would get a different kind of result. So what would the results look like? Well, let's see. Here's an equation. It looks like the left-hand side could get simplified a little bit before we start using inverse operations. I have a 5x and a negative 5x. They're like terms. Those are actually inverse like terms, though. So when you add them together, they just kind of cancel. They undo each other. So the left-hand side becomes 3. The right-hand side becomes 16. We have no job left to do. We can't find x anymore because it's been completely eliminated on its own. And 3 does not equal 16. So it's not telling you x is either of these things. It's telling you this equation boils down to something that's false regardless. So when you get a result like that, you have an equation that is not true. No solutions are available to that thing. What would it look like if the equation was true no matter what value was used? Well, you don't know that right now when you look at this equation. But if you went through the process of cleaning up the left side or right side, or both in this case, and the left side becomes 4x plus 24, and the right-hand side becomes, I see some like terms there. In this case, a 2x and a positive 2x on the same side, they will combine and they won't cancel each other. That becomes a 4x on the right-hand side, and 24 comes down. And now I have suspicions that this seems to be an unusual case, but let's not panic. We'll try to remove the variables from one side by subtracting 4x, balance it on the other side, and the variables disappear from both sides. So the result here is that 24 equals 24. So once again, it's not telling you that x is anything. You've learned, because the x completely disappeared all on its own, you learned that this equation was equivalent to 24 equals 24. So when I ask what x value makes this true, the answer is it was true to begin with. So let's say every x value would work. Over here, what x value makes this true? This thing was false to begin with. So no x value makes it true. So those are the two kind of more unusual results. So we've taken a look at some main ideas, and then your assignment today is going to be to try a handful of problems, and it's going to be from different chapters, but these big overarching ideas are all you should be taking away from these linear equations.